All right, so now we're going to do an example. We are going to find, so first let me go ahead and write this out. This will be our first example. We are going to find a general solution okay, a general solution to the following differential equation. Okay, that looks terrible. Equation as such. Okay, and that's going to be 2y double prime plus 18y, okay, equals 6 times the tangent of 3t. Okay. So first, since the formula for variation of parameters requires a coefficient of 1 in front of the second derivative, right? Let's take care of that before we forget by dividing 2 across the entire equation. And so the differential equation that we'll actually be solving is given by the following. That'll be y double prime, so this implies, plus 9y equals 3 times the tangent of 3t. Okay? And I will leave it to you to verify that the complementary solution for this differential equation is given by the following. Y sub c of t, the complementary solution, is equal to c sub 1 times the cosine of 3t, okay, plus c2 times the sine of 3t. Okay, so you have to dig deep back into our previous notes and you'll find how we can find complementary solutions very simply and very easily to get this form. So this is what we end up having. We have y sub 1 of t equals cosine of 3t. Okay, that's a t. And y2 of t is going to equal sine of 3t. Okay. So now all we have to do is compute the Wronskian to make this very simple for us, because it's also part of our formula that we derived previously. So the Wronskian is going to equal the determinant for the following formula and equation. So it'll be cosine of 3t, sine of 3t. I'm sure you remember this. And this will be minus 3, because it's the derivative, minus 3 sine of 3t, okay, times 3 cosine of 3t, which was the derivative of sine 3t above it, okay, and we are taking the discriminant of this, so this is going to equal, when all is simplified, it'll be 3 cosine squared of 3t, okay, plus 3 sine squared of 3t, and this all actually equals 3. And the reason why is actually because, if you remember generally, sine squared of t plus cosine squared of t is actually equal to 1, right? You remember this? So if I was to factor out a 3, right, this gives me cosine squared of 3t plus sine squared of 3t. And this happens to all cancel out and become the number 1. And that's why we get 3 as the answer to our Wronskian. Okay? All right. With that out of the way, we can now use our formula to find the particular solution. So the particular solution is then, it's going to be capital Y, capital P of t, okay, equals negative cosine times 3 of t, this was the y1 designation we had, times the integral of 3 sine, okay, 3t times the tangent of 3t, okay, all divided by 3. This is a t here. No, it's not really easy to see, is it? Let me go ahead and rewrite it. There you go, 3t. All divided by 3 on all with respect to t, okay? And I'm going to add this to y2, which we called sine of 3t, okay? And this is going to be multiplied into the integral of 3 times the cosine of 3t, okay, times the tangent of 3t, all divided by 3 dt. Okay, so that's the result of using the formula directly with our designation for y1 and y2. And again, let me reiterate, it doesn't matter which function is y1 or which function is y2, you will get the same answer. All right, so simplifying this, we get the following. So this all implies we get negative cosine of 3t multiplied to the integral of sine squared of 3t, okay, all divided by cosine of 3t with respect to t. This comes from using the definition of tangent, which is sine over cosine. And this is going to be added to, and I think I have room, added to sine of 3t, okay, multiplied by the integral of sine of 3t, okay, dt, just like that. Alrighty, and so going further, this will become minus cosine of 3t times the integral, and this is where things become really interesting. Because I want to simplify my integral from the previous case, namely this one, this integral I want to simplify as much as possible. So recall that property that sine squared of t plus cosine squared of t equals 1.